Okay, so because the period's been different lengths, you guys got to different places. So we're going to start right here. You should have got these down, right? And we talked about the power plant. And the power plant having three distinct areas. One is the reactor core, one is the steam generator, and the other one is the cooling system. Okay? In the reactor, remember there's the reactor core. It includes control rods, fuel rods, and a moderator, which is, for the most part, ones we've been using, water. Okay, so then we get to nuclear fusion. So fission is what we use in the nuclear power plants. Nuclear fusion is a reaction that requires a very high temperature to start. These are what happens in the sun and in nuclear bombs. So nuclear fusion is taking two elements and fusing them together into one. So all you need to get was it was high temperature. It needs to occur at high temperatures. Okay, so nuclear fusion is joining together of two light nuclei to form larger nucleus. That's what you need for fusion. So write that down. You don't necessarily have to have the rest, except for the bullet after after the equation. A neutron and a large amount of energy are usually produced with fusion. So usually at least one neutron and large amounts of energy. Fusion is not currently usable because we can't control it. Okay? You have to have very, very high temperatures and very, very high pressures. And so we can't control it. We don't have that ability right now. It's like trying to control the sun at the sun's level. So going to the sun and being able to be with the sun. Yes? Yes, there's a whole bunch of them up here. There's also multicolored ones on your desk. Oh, okay. All right. So going forward here, nuclear fusion looks like this. So you take a big particle and it splits into two smaller particles and it makes it into one bigger particle. I'm thinking fission. So fusion, we're putting it together. We're fusing things. So when you hear fuse, that means putting together. And I did give you that little diagram on your paper so you didn't have to draw it. Okay, so that was the end of last time where we were supposed to have been. We're starting this time. I like this commercial or this cartoon. Good news! We got the last batch of radioactive isotopes in Ontario for your medical treatment. Bad news. It was a little strong, or a little bit strong, because he's glowing in bed. Ha ha ha. Okay, so we're going to talk about today some misconceptions and hopefully get them cleared up. Is irradiating food safe? So the process, whenever you see this symbol on a package, that means it's been irradiated. Okay, there's multiple uses for it. To prohibit things from growing, like onions, potatoes, ginger, and garlic. We don't want them growing when we're trying to sell them because that makes it go bad. Insect infestation, so if I have weevils, it'll kill the weevils in the wheat and we can still use the wheat. Cereals, dry foods, stuff like that, so we want our Lucky Charms to last a little bit longer. Shelf life of meat and poultry and fish, and pathogen reductions in spices and things like that, and fresh fruit. So we're going to listen to this first one up here for a minute.
Remember the spinach scare? What about the one at Taco Bell? Those recent E. coli outbreaks might have you worried about what you're feeding your family. Some say radiation is the answer to all those problems. But is it safe? 2 more suspected cases of E. coli contamination.
This subject has been in the news a lot recently. It's an E. coli outbreak.
The outbreak has spread to at least 19 states, is being blamed for 1 death.
Recent reports on foodborne illness in the U.S. have many consumers up in arms about food safety. Fears that some experts say can be prevented. With the use of a treatment called irradiation.
We expose foods to this very high energy source, and that causes ionization of DNA. So effectively, we're killing these bacteria by damaging their DNA.
Students at Iowa State University, one of the country's 2 teaching facilities, learn the process.
Now just push it all the way up to the stop.
In their own treatment center and university labs where bacteria is analyzed.
We have 2 plates showing the bacteria that have resulted after 24 hours of growth. The radiation would have reduced that to non-detectable results.
Irradiated foods are available in stores, usually costing a few additional cents. The process is FDA approved, and with 5,000 deaths a year attributed to food bacterias, like the E. coli virus, some argue all food should be irradiated. But consumer advocates like DC-based Food and Water Watch say not so fast.
We need to be doing a lot more to make sure that we're growing clean food in the first place rather than treating it with these really harsh, dangerous technologies to try to fix it at the end of the line.
But proponents like Dennis Olson stand by the technology.
There's no question that it is safe.
Ultimately, consumers will decide.
Madeline Fernstrom is today's diet and nutrition editor, as well as the director of the Weight Management Center at the University of Pittsburgh. Madeline, good morning to you.
Good morning.
As we saw in that spot, several E. coli scares in recent months in this country. If irradiation can get rid of the E. coli, get rid of the problem, then why aren't we seeing more products in the stores that have been irradiated?
Because as you say irradiated, and what pops into your mind? Radioactivity. It is absolutely untrue. Food irradiation is another word for cold sterilization. We think, for example, with milk, it's pasteurized and it kills off all the bacteria with heat. We would never think of drinking unpasteurized milk. Similarly with raw food, with meats and produce, that cold sterilization, that is food irradiation, just takes energy rays and is exposed to the food and then kills off most of the bacteria. So it's very safe. And I think if it were called cold sterilization, more people would embrace it.
So these waves essentially just pass through the food? Is that how it
right,
works?
Right, it passes through the food. Think of this sort of like microwaves, like we have in a microwave oven, but it doesn't cook the food.
So it's essentially bad PR then? If they called it cold pasteurization, you're saying people would have no issue with it?
Well, here is something that a recent Purdue University study showed, that if you gave people a short introduction about what this would be doing to food and how it would protect the food supply, 9 out of 10 people would decide, okay, I'd really try that. And that's a good thing. There's a lot of misunderstanding. And of course, when one hears about, well, maybe we should just protect the food supply, well, why don't we just get to the root of this and get rid of all the bacteria?
That's a good point, though, Madeline.
And I appreciate that. The issue is, in a perfect world, that would be wonderful. But I think that cold pasteurization, food irradiation, can be a good tool to help keep the food supply safe. It does not replace good manufacturing processes.
There are some special interest groups who say that sometimes this irradiation can chemically alter food and create things like carcinogens. Now, the FDA and the CDC have said that's not true. The food is safe. Who's right? Who do you believe?
Well, we have to go with more than 40 years of scientific data. People worry about these things. The FDA, the CDC, and scientists working in this area. It is absolutely safe. And the fear of and opinion about this can't really supersede the ability to say we need to keep the food supply safer and try and kill off as much bacteria as possible.
Doesn't it with certain foods actually change, though, the texture of the food and possibly the taste of the food?
Now, of course, food irradiation can't be for everything. We really want to look at, things that, like potatoes and onions and some of the fruits and vegetables, that can have a change in texture and perhaps in taste. And it may not be for some of these things. Certainly for raw meats, poultry, pork, lamb, and you can even purchase some already packaged. And there's an international sign for
What
food
is the sign? How do you know
irradiation.
if your food has been irradiated?
Well, because there's a sign that is agreed upon that's on the food. And I have to tell you, we did have a little trouble in sort of the Pennsylvania, New York, and New Jersey area finding some of this. But we did get some examples. And hopefully we'll see some more of these foods once people understand this can really help to keep the food supply safe.
At this point, just so I understand, because I don't think I've ever run into this symbol in my supermarket. Maybe I just haven't been aware of it. But how much food right now in this country is irradiated?
Well, very little, and I believe an estimate is about 1% of the food is irradiated. Now, it is approved to be irradiated and then sent to the supermarkets. But the debate really goes on: will consumers purchase this? The cost issue is not significant; it's just pennies more. But also, there can be a lot of savings in produce if it's used for that, because spoilage is less. You can have a longer shelf life, which can be a help, and much less food wastage.
But bottom line, whether your food is irradiated or not irradiated, you still have to practice healthy preparation at home.
Once the food gets home, you still have to wash your hands, not mix raw and cook things. It's only going to protect it coming from the farm to your house, and then you still have to use safe practices, and the same with restaurants.
Okay, irradiation does not equal radioactive.
No, it's a safe thing and good to kill bacteria, keep the food supply safe.
Madeline Fernstrom, as always, thank you very, very much.
Okay, you have 3 boxes on your notes. Would you fill in what you can so far? And in about another minute, I'm going to start the next video. for you. So fill in what you can with the 3 boxes. So keep filling in the boxes as you listen to this next video.
Electromagnetic radiation covers a broad spectrum of wavelengths and includes sunlight, which is vital to life on Earth. The waves have different uses according to their energy. Radio waves enable us to communicate and share information. Microwaves cook our food. Infrared radiation warms us. Visible light illuminates our lives and is essential for food production. Ultraviolet radiation gives us suntans and bone-strengthening vitamin D. X-rays enable us to diagnose and treat illnesses and to check our luggage. And gamma rays are used to sterilize medical equipment. Irradiation using X-rays and gamma rays can also be used to treat food. By choosing the right wavelength and dosage, these rays can prevent sprouting of vegetables like potatoes, maintain their freshness and taste, and destroy harmful bacteria that could be present in spices, meat, or seafood. Also can rid fresh fruits and vegetables of insects that might otherwise hitchhike, spreading to other regions of the world, where they could have devastating effects on the environment and agriculture. Food irradiation involves shining electromagnetic rays or beams of electrons onto food. The energy is transferred at an intensity necessary to give the desired effect. It is a cold process, so spices retain their unique flavors and aromas that would be diminished by heating. It also avoids reliance on chemical methods, such as fumigation or pesticides, to combat bacteria, insects, or other spoilage organisms. In addition, those irradiation beams pass through packaging, so the food remains protected from bacteria or insects after treatment and will remain fresh longer. Food irradiation offers a chemical-free and heat-free approach. It maintains fresh food quality, reduces the risk of foodborne diseases, and prevents the spread of exotic insects through globalized trade.
Okay, so there's a couple of things I wanted to point out in that video. They talked about if we use food irradiation, we don't have to use fumigation. That's the way that they're right now stopping bugs in things. So I would rather have the food irradiation than chemicals left over residue on my food. There's also, we heat pasteurized milk right now to get rid of the bacteria in it. But not everything can be heated to be pasteurized, to get rid of the bugs. So this gives us another way to do it. So is it safe? What do you think? Thumbs up, it's safe. Thumbs down, it's not, from what you've heard today. Okay, good, it is. It's safe. And the thing that we need to really worry about here is like the lady said that was being interviewed. She said, it's just the choice of words that they gave it. If they would have said not irradiated, because that sounds like, the Hulk got irradiated, we're all going to turn green. So it brings up to people's, in their minds, it brings something like it's going to genetically damage me. But actually, it genetically damages the bugs and whatever that's on it so that they are gone. But it doesn't stay with it. Okay, so is it safe to eat? Yes, it is. Radiation kills the foodborne pathogens without significantly affecting the nutritional value of the food. There are some fruits or vegetables, when they're irradiated, just don't taste the same, but it's not enough that if you didn't know which one was irradiated, you wouldn't know the difference. Does that make sense? Okay. If you were told, then, oh yeah, I can taste the difference, kind of thing. It does let us get, like I was telling you earlier, strawberries from one side of the country to the other side, because otherwise they would go moldy and bad in a couple days. And you can definitely tell those grocers that have strawberries that have been irradiated and those that haven't, because the strawberries that have been irradiated stay nice and pretty and look gorgeous for a longer period of time, where the ones that haven't, they start to decay. All right, so detecting and measuring radioactivity. Radioactivity cannot be detected by the senses. You can't see it, you can't feel it, you can't touch it, but it still has a very powerful effect. Nuclear radiation will damage or kill rapidly dividing cells. So that's why we like it to do for bugs. It'll also do that for humans in bone marrow, skin, and the reproductive and intestinal systems. So for those people that are irradiating our food, we need to make sure that they're doing so in a safe way. Cancer cells also rapidly divide as well. So that makes radiation a very good treatment for cancer cells. They're pinpointing it better and better. Food is I cannot say that word right now. Irradiated. Exposed to gamma radiation to kill off any living organism on it so that the food will last longer and will not be contaminated. Afterward, the food is not radioactive. That's what a lot of people think. It's radioactive. Oh my gosh, you're going to eat it and you're going to become the Hulk. That doesn't happen. It just gives it a longer shelf life. So like we were talking about Gosner milk that can be left on the shelf. That's one of the things that could be irradiated. Forgot I finished that one. Okay, we okay to go forward? Okay. All right, so we're going to do a cloud chamber lab. The cloud chamber was invented by an English physicist, C.T.R. Wilson. It sort of sounds funny because, anyway. In 1911, it was an instrument designed for to study the trails of radioactive elements. First, I have already saturated the air in a petri dish for you with isopropyl alcohol, 91%. When the high energy particles from an alpha or beta decay go through that and it's been cooled, it actually makes a cloud on the path that they took. Okay, so and that's because when high energy particles flow through the air, electrons are knocked loose and some of the atoms and they form ions, and the ions act as a attractor for condensation. You can see the path. So this is basically the setup of a cloud chamber. We're not going to use the pin. We're going to use a thorium mantle instead. I think you get a lot better results and you can see a lot more with it. And my dry ice is not going to be crushed up because it stays longer and I need it all day long. So it's going to be in a block. But other than that, you're basically going to have this. We're going to shine. It shows a 45-degree angle here, but I want you to shine it in through the side at a 45-degree angle. You'll see it a lot better because the tops of the Petri dishes are getting scratched up, and so it reflects the light really weird. But if you shine it in the side, you can see them really well. Okay? The cloud chambers detect the paths taken by the ionizing radiation. It sort of looks like, you know, if you ever look up at the sky in the summer or even sometimes in the winter, and you can see a jet path but can't really see the jet. Have you ever done that? So you can actually see that pathway that it's been on. That's what we're going to be seeing. We're not going to be seeing the jet at the very end, but we're going to see the path it took. Okay? There's 3 types of radiation given off. There's alpha particles. Those will be the ones that are straight and they're fatter. You're going to be able to see them really easily. And then there's beta. And beta is high speed, and they sort of do like an arc because they've got a charge. So they'll sort of arc. So what you're going to see, gamma rays we won't see. Now this one I'm going to show you an example of right now. This is all alpha particles that you'll see, okay? So we'll get this started hopefully. Come on. Doesn't want to start. Let me go over here and get it started. This one is a very strong alpha source. We're going to see a lot of the alpha sources when we go back to lab. It won't be that big because we'll have the mantle in the center, and it won't be necessarily that strong, but we had some going pretty good first period. So you can sort of see. Remember that paper will stop alpha, right? So we're not really worried about it. We are going to be wearing our goggles, though, just because that'll give some slowing down. You know, it's like trying to get through something if something's stopping it. Okay, so that's sort of what we're looking at. So let me show you what you're going to be seeing. So the alphas will go straight. Now you probably can't see them real well. The betas are harder to see. But I'm going to show you and then I'll back out of it. So there's a beta right here. There's a beta right here. And I think I've got one more right there. And there's actually one right there if you can see it, a couple of them. They're harder to see because they're smaller. And because they're smaller, they leave a smaller pathway. So you're probably going to, I'm going to back out of this. Can you see where they are now that I've pointed them out? Okay, so you're going to be watching for them. They're hard to see. And if you see them, great, wonderful. But if you don't, at least you'll get to see the alpha. The alpha is pretty strong. Okay? But the alpha is a lot bigger. It's mass of 4, where beta had a mass of 0, right? And it's a -1 electron. Okay, so we're going to go back and do that. Bring this up. It doesn't really show, but that's okay. We are going to have a test next time. So, I forgot to fix this. Test you! Yeah, we're going to have a test next time. So make sure that you have got the things that you need. I've got 3x5 cards up here, and you can go over them. I'm going to bring up your part of the review that's next and the lab, and we're going to do some of it together. I know that just hurts your feelings that you don't want to do it all by yourself, but I'm going to show you how to do some of it. So let me get to where we start. Okay, so we're going to go back and we're going to have a thorium lantern mantle that looks like this, and we're going to draw what we see. So when we go back to lab, that's the part you're going to do. Okay, that's basically it back in lab. And then what particles do you think you're observing? So when you get back there, if you just see straight lines, it's alpha. If you can see some of the curved lines, it's beta. Okay? So on this next part right here, we're going to practice writing equations. This is still part of the lab. I'm going to do a couple of them with you. So let's do this first one. Uranium-238. How do I write it? Big U, 238. What number is uranium? Down in the F. 92, right? Okay, is decomposed means arrow through alpha emissions. What's an alpha? 4,2 helium. Good, I heard it. And I'm done, right? No, what do I need to do? I need to add something on this side because the top on one side has to equal top on the other side. So what do I put on the top? 234. What do I put on the bottom? 90. What is number 90 on the periodic table? Thorium, and I'm done. Okay, so you've got a few to do here. Now let's go down to number 2. And this doesn't stay with that when I move it up, so sorry about that. So number 2 actually goes on to 2 pages. So you've got A, B, and C. I'm going to show you what you do in A. You do the same thing in B and do the same thing in C. D and E ask questions about A, B, and C. Okay? All right, so this is what you do. This is a decay series, a small one. So we're going to start with lead 210. So 210 goes on the top. Lead is Pb. What's on the bottom? It's in the P block. 82, good. Decomposes by beta. So decomposes is the arrow. What's beta? 0, -1. And I could put an E or a B, whatever. Is that it? No. And it says in 21 years. So I'm going to put the 21.0 years on top of the arrow because we're going to need to use that for E and F, or A, B, C, D, and E. Sorry. So I'm going to put plus. What do I put on top? 210. What do I put underneath? 83. What number is 80? Or what element's 83? It's what? Bismuth? Bi? Okay. Then I take bismuth. It says then the product. So I take bismuth and start at the beginning again. Bismuth, Bi, 83, decomposes by beta emission again, 0, -1, beta, but in 5.01 days. So am I done? No, I got to add something again. What do I add? 210 again. What's on the bottom? 84. 84 is what element? Polonium. And then it says again that product, so I bring polonium over here. Decomposes by alpha. What's an alpha? 4,2 helium. And 138, let's try that, 0.4 days. Plus, what else am I going to have on the far side? 206, and what's on the bottom? 82. And it should be lead again, but a different isotope of lead. So you're going to do that for B and C, and it'll tell you how much. You want to make sure that you're keeping these in the center because it will ask you in D and E which one's the longest and which one's the shortest pathway. And if you put these down the center, you don't have to go back into the paragraph to try and figure it out. Okay? Just a little help. All right, so then we're going to go farther on. I'm going to give you little hints on each thing here. So going. So there's which pathway took the most, which pathway took the least. What's the purpose of the dry ice? What did I tell you was the purpose of the dry ice? Do you remember? Oh. So I've made that cloud chamber and I filled it with alcohol. What does the dry ice do? Yeah, it cools that down so that when the alpha or beta particles go through, it will condense on the pathway. If it's not cold enough, it won't. Okay, and so this next two parts right here, kids kept asking me last period, you're just describing what happens. So how does an alpha, when I get an alpha decay, what happens to the element? Well, for an alpha, I lose 4 in the mass and I lose 2 in the atomic number. For beta, I lose nothing in the mass, but I gain a proton, right? The atomic number goes up. What is K capture or electron capture? That's putting a beta on the reactant side. Okay? When does it occur? Well, any radiation or any kind of decay thing happens when I am unstable. Okay? What effect does it have on the nucleus? Well, it's on the reactant side. I've got a beta, and so I'm going to reduce the number of protons I have by 1. And then what is a gamma ray? You should be able to get from your notes. What is a positron? Remember, a positron is 0 plus 1 beta, so you're going to tell me how that affects the nucleus. Okay? And now we get to this page. So everybody go to this page because it's important we do this one together for a little bit. This is a very long decay series. This is what happens in a nuclear reactor. this is why it takes so long to get it to something that is not causing problems. So, first thing, we start with uranium-238. So 238, and uranium was what number? 92. This will tell me what decay it's going to undergo. So here it's going to undergo alpha. So I'm going to go 4, 2, and I can either put alpha or helium. You choose. And I'm going to get what else? 234. And bottom number? 90, which is thorium. Okay, then I'm going to bring that down here. 234, 90, thorium. Gives me a beta. What was a beta? 0, -1, right? Plus what? 234, and the bottom number? 91, and 91 is? Protactinium. So then I bring protactinium down here. 234, 91. Protactinium undergoes beta decay. We've got this, right? Plus what? 234, 92. And 92 is uranium. And then I would take that and I would keep going like that. You get the idea? Okay, so now I'm going to change pages here, and I'm going to have you help me with this next part, because this page and the next page relies on this page. If it were me, I would check with my neighbor. Is this what you got for the next one? Is this what you got for the next one? Because if you mess up on one in this series, it screws everything else up past it. Yes? Positron is positive. These are all betas. So the decay is alpha, beta, beta, alpha, 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 beta, beta, alpha. Okay? All right. So, whoops, that's not what I wanted to do. Let me get back to where I was. I wanted to erase, and I grabbed the wrong thing. Okay, let's go down. Next page gives you this lovely little graph here. What did we start with? On the other page, what do we start with? Uranium-238, right? What was uranium's number? 92. So right here at 238.92, I'm going to put a U for uranium. I'm going to circle it. That's where I'm starting. What was my next daughter? 234 and 90, and it was thorium, right? So I'm going to put TH here. I'm going to circle it. I'm going to connect these two. Okay, what was my next one? 234 what? 91 what? What was the symbols? PA? Protactinium right here. And I'm just going to make sure they connect. And then my next one was uranium, right? But it was still 234, right? So I put a U here and I connect it. And then I just keep going. Okay, I'm going to give you a hint on this. You should end up with a lead, 206, at the very bottom. So you might want to put yourself a little hint. If you don't end up with lead 206, you probably did something wrong. Okay, lead 206. All right, so then, I'm going to erase this, maybe, if it'll let me. Coming down to the bottom here, whoops, right here. This right here down at the bottom just tells you that you need to put that stuff in the diagram, just like I said here. Put some lines here and say end of lab. So you know that up to that point, you're going to, from where it starts the cloud chamber to here, that's going to be your lab that you're submitting for your lab for the 50 points. Okay? Now, this part right here, this is also part of 12.3, daily work. Okay, so what we did in lecture before and then after the lab is going to be daily work. Got it? Okay, if you look at the daily work, okay, it should be fairly straightforward. You're just plugging in numbers for equations. You're writing equations for me. You're talking about half-lives. We've done half-lives. You're telling me what particle you think would be which one. Okay, alpha, beta, gamma, positron. Radiation sickness can be caused by, it just has questions from what we did in lecture. Okay? So then when you're done, submit it and you're done. So let me tell you a little bit about this lab before I take you back. It'll take me probably 15 minutes to set up. Then it takes about 15 minutes for the air to cool down because I've got to get the dry ice back out. When it's ready, I'll make sure it's working. I'll say, okay, it's time to go see it. We'll just drop what we're doing. We'll go back and see it. It takes 5 minutes to draw your little diagram. Then you come back and keep working. So it's a work day, basically. Okay? Questions? Make sure you get everything in by May 14th, guys. It's coming down the pike. We're at May 3rd. 11 more days, and everything needs to be in. So if you've got stuff missing, now's the time to get it in. Okay? All right, I'm going to go set that up. I'll put this back up for you. Don't forget, test day is next time. I've got 3x5 carts on the computer cart that you're more than welcome to use. Oh, there was one other thing I wanted to show you really quickly. Let me do that. If you go into Canvas, bring Canvas up here real fast. Okay, if you come in, whoa, hello. If you come into Canvas, okay, and you come down to, I don't care about Smart Ink, go away, it's being dumb. It won't let me do anything without, okay. So this is the nuclear chem that we're in right now. If you go right below it, there's end of year project. If you go to end of year schedule, everybody watching? This is important. If you go to end of year schedule, under that it will tell you what we're doing every day till the end of the year. It will tell you what presentation, who has what presentations due, and what day they're due, and what order you're presenting. Okay? So, make sure you're checking this. Make sure you do not procrastinate your project so that you're ready. Now, on the day that we have 4, we only have an hour and 20 minutes, so it's going to be divided by 4 to get there. So whoever's first, you want to be here and ready to go right at the bell. Does that make sense? And then you only have a fourth of the period. Okay? Any questions? All right. Then go ahead and get going. I'll just leave this up to remind you, and I'll go get that lab set up. Okay? You don't need to do any more? Okay. Then we just get this other thing up.
So there's 3 different
So the test is next Tuesday. So Thursday. Did you? Yeah, it's like, just said they were, but you can burn them off with dry. And she says, you want to do it on your own, I can charge you $130 for it, or I'm like, I will just go get some dry ice and do it myself. Thank you. Okay, they actually started early, so come on back, grab some glasses, and just get around. It's just down the center aisle, so get around a cloud chamber. What? This is the lab. We're doing it right now. You'll need at least 2 people. picture. Yes. But you gotta make sure you look at the rubric. Everything done. Yeah, you can do a rubric, or you can do PowerPoint, you can do a video, you can do a Prezi, you can do. Okay. You could do a skit. Actually going to take a bit over here. and I'll get the solution out. But basically, these should be about 3/4 full of solution. So number one, if it doesn't have it, then we need to worry about that, undo them. You'll need to wear goggles. You can wear gloves if you'd like to. Then we need to take this out with some distilled water in one of the squirt bottles. You're going You got to be really careful though with this because it's very thin glass, and so there's some test tube brushes back in the back, just really soft on it. Okay, I'll go get my keys and go get the buffer out, and I'll just set these on that back. Okay, so we're working hard, right? We want to get everything in, make sure we turn everything in for this unit, and do a good job.